A related concept is that of a relative rate of change. A relative rate is a normalization of the differential, something of the form du over u. This is telling you something about what percentage change you have. Notice it is unitless, and notice you could also get it in terms of the log of u. Let's put this idea to work. If we have a voltage across a variable resistor that is fixed, then how are the relative rates of resistance and current related? So in a simple circuit with voltage potential V, current flow I, and variable resistance R, these quantities are related by Ohm's law. That is, V equals I times R. Now, if we differentiate both sides of this equation, we get dV equals R dI plus I dR. And now, to compute the relative rate of change, we look at dV over V. That must be 0 since the voltage is fixed. So, dividing the right-hand side by V gives us what? Well, R dI plus I dR over I times R. That splits up into dI over I plus dR over R, meaning that the relative rates of change of R and I are inversely related. Let's look at an example from geometry. How does the relative change in volume relate to that of surface area? In the specific case of a solid ball of radius r, how do the volume and the areas compare? Well, the volume is 4/3 pi r cubed. When we differentiate that, we get dV equals 4 pi r squared dr. Now, for surface area, that function is 4 pi r squared. Differentiating that gives dA equals 8 pi r dr. Now, to look at the relative changes, we must take dV over V and divide that by dA over A to compare these relative rates. What is that? Well, that is going to be 3 dr over r over 2 dr over r. With a little bit of algebra, you can see that it's a constant, 3/2. I wonder if that holds for any other shapes. Let's take a cube of side length s. The volume of that cube is s cubed. When we differentiate, we get dV equals 3s squared ds. The surface area is 6s squared. Differentiating yields dA equals 12s ds. If we again look at dV over V and compare that to dA over A, we're going to get 3 ds over s over 2 ds over s. The relative rates of length cancel, and we get, again, 3/2. That means the relative volume change is always 150% of the relative area change. I wonder if that has any meaning. Well, let's go back to economics and consider the important questions. That is, what is the difference between milk and wine? Well, it is in elasticity of demand. If P is the price and Q is the quantity demanded at that price, then the elasticity, E, is defined to be the rate of change of the relative demand with respect to the relative price. That is, dQ over Q divided by dP over P. We're going to put a minus sign in front of this since price and quantity are inversely related. When we do so, what do we see? Well, the higher the price is, the less you want something. The lower the price, the more you want. But it depends on elasticity. If E is between 0 and 1, we say that demand is inelastic. Changes in price don't change the quantity demanded so much, like milk. On the other hand, if E is larger than 1, then this is called elastic demand. If wine goes on sale, I'm more likely to buy more and then store it. That doesn't work with milk. Now, when E is equal to 1, it is called perfectly elastic. Note that it is not slope, but rather relative rates of change. Here's a question. How do you maximize the relative revenue with respect to relative change in price? Well, R, the revenue, is the price times the quantity, P times Q, or the area of this box, if you like. Then, differentiating this, we get dr equals P dq plus Q dP. Looking at relative revenue is dr over R. We've seen a very similar computation with our electric circuit. We get dq over Q plus dP over P. And now, looking at the ratio of relative revenue to relative price gives us what? dq over Q over dP over P plus dP over P over dP over P. That latter term simplifies to 1. The former is negative E. So we have maximal revenue when the elasticity equals 1. So, concluding, what do we mean by dx and du? There is much more to the story than what we have said. For now, differentials are functions that implicate rates of change. When you get to multivariable calculus, you'll learn a different perspective involving differential forms.
We've seen in this lesson that thinking of derivatives from a more abstract perspective, that of differentials, is very useful in several application domains. We will continue this process in our next lecture by thinking of differentiation itself as an abstract operator. In this more rarefied setting, we'll see that it deepens our understanding and leads to better computation as well as comprehension.